Okay. We'll start there. Okay. Um, Basic algebra, these are all the things that if you had algebra, you probably learned. We're supposed to remember the names of them, which I never could. But essentially, they're how you manipulate the variables. I want to get rid of him.
Top left, you could pick the little top left of your picture. You can pick the little minimize button. And your picture.
But it's hidden.
Oh, upper left-hand corner of your picture. Picture and picture. Yep, go to the left.
Oh, this one?
Yep, all the way to the left. You see the minimize button?
Oh,
Yep.
There we go.
And then you can drag it down. Drag it down.
All right. It's good I got a Zoom person. Okay, so you got basic addition of letters, variables, so that x plus z is the same as y plus z. You can subtract, similarly, you can subtract a number from both sides of an equality. And I guess I should start with, it all assumes that you have an equality of a equals b or x equals y, and how you can manipulate that so that you can add something to both sides, you can subtract something from both sides, you can multiply both sides by the same value, you can divide both sides by the same value. This one was confusing, but a number is always equal to itself, which is sometimes important. The order doesn't matter. Okay. So if x equals y, y equals x, to transpose them. What are we doing here? Okay, if x equals y and y equals z, then x is going to be equal to z because they're essentially both equal to y. You can substitute. So if I know that x is equal to y, then you can substitute in an equation, not really an example here, where if I had x equal to z, I could substitute y for x, and then y would be equal to z, and whatever that equation or value is, you could substitute. And also the square root of both sides are equal. Oh, another one. Samantha, introduce yourselves.
Lucia.
Aaron Marsh. Steve.
And you're being recorded. You know your algebra? Okay, good. I won't go over it again. You're too young to forget it. Okay, some examples, and I'm using what we'll get to later is Ohm's law. And if you take one of the basic Ohm's law formulas where E, or electromotive force, is equal to current times resistance. If I wanted to solve that equation for current, okay, I could divide both sides by the resistance and wind up with the voltage divided by the resistance equals the current, or with that other one we talked about, flip them around and I is equal to E over R. Likewise, if I wanted to solve it for R, I divide both sides by I and do the cancellation here. And I come up with E over I is equal to R, or R is equal to E over I. And those are the three basic Ohm's law equations that you'll see. And a lot of times, and I've got one on here later, you'll see a little pie chart where you have E on the top and then I and R on the bottom, where, so you don't have to remember the formula, you put your finger over the one you want to solve for. So if you put your finger over I, you got E over R. If you put it over R, you got E over I. And if you put it over the E, you get I times R. So it's a little quickie that helps people remember that can't remember formulas, like when you get old. Same thing, with the power equation, where power is equal to current times voltage. And we do the same thing to solve it for I or solve it for E. And here, we're going to do a substitution. So we know that I is equal to E over R. So I'm going to substitute for I with E over R. And the E's multiply, so I get E squared over R. There's another pie chart for this one also, where you do the same thing with power, current, and voltage. And a lot of times you need to solve it for voltage or current. And those, if you notice, are always a square function. And that'll come up a little bit later when we talk about decibels, on why when you're doing decibels on voltage or current, it's 20 times the log as opposed to power, where it's 10 times the log. It's because of the square function. This is another showing a substitution on how you get from this formula back to Ohm's law. This is sort of called Watt's law, after James Watt, who, steam engine guy, developed stuff for power. Again, another substitution or multiplication, converting back to one of the standard Ohm's law formulas. Any questions?
I guess remembering order of operations would be helpful here, where you got to do the equation in the parentheses first, and then.
Yeah. And I do much better on questions than just sitting there talking. So feel free to question anything, even if I'm wrong, which I could be. Okay, exponents. Everybody familiar with exponents? Okay.
This is way over my head.
It's just a way to represent powers of a number. In this first one, okay, I took the variable a to the 0th power, which means in any number, when you do an exponent, to the 0th power is going to be equal to 1. If you take it to the 1st power, you're multiplying it by 1, so it's going to be equal to itself. The 2nd power, which we call squaring it, but it's multiplying it by itself. The 3rd power, it's multiplying it by itself. And on, so a to the 4 would be a times a times a times a. You don't normally see it like that, but I was trying to show you how it works with a variable as opposed to a number. We normally deal with it in powers of base 10. So 10 to the 0 is still going to be 1. 10 to the 1 is going to be 10, the same number. 10 squared is 10 times 10, or 100. And 10 cubed is 10, 10, 10, 1,000. 10 to the 4th is 10,000. 10 to the 5th is 100,000. 10 to the 6th, which you see a lot, is megacycles. Or Now, in part 2, where we talk about digital stuff, we do things to base 2. So you take the number 2 to these powers, and you get 2, 4, 8, 16, 32 on up. That's when we talk about digital logic. Now you can also have negative exponents. So if you take a number to its -1, that's just the reciprocal. And if it's to the -2, it's the reciprocal of the number squared. -3 would be the reciprocal of the number cubed. Examples are with 10. Okay, be a tenth, it would be 100th, it would be 1,000th. On like 10 to the -6 is going to be a millionth. That would be like a microfarad, how we represent that. And we do it in base 2. You're going to get a half, quarter, eighth. You just keep dividing. Clear as a bell? Clear as mud.
No, it's pretty clear so far. When we take the exam, I'm assuming we can't bring a cell phone and bring like a scientific calculator or.
Yes, you just have to show that it's erased. Which can't have any calculations on it.
Okay.
Depending on where you take the exam, you can bring a blank sheet of paper to some. Others insist that you write on the back of the answer sheet. Do not, in any of them, unless it's online, write on the answers on the question sheet because they reuse those.
Okay.
The recommended, and bring mine. The recommended calculator, particularly when you do advanced or extra, is the TI 32 Roman numeral 2S, I believe it is. It's around $13, $14 at Walmart. It's one of these solar powered ones, so you don't have to put batteries in it. You just have to show it some light occasionally. And it'll do everything you need, and it's easy to use. And I might caution you that there's an earlier version. It's still a TI 30. And that one tripped me up because when I took my extra exam, I forgot my calculator. And you only really need it for 1 or 2 problems, depending on your test. And there was one that I got on the exam that I always worked it with my calculator, and it was easy. So they gave me a calculator for the exam that was the older model. It's TI 30.
Mm-hmm.
It didn't work anything like mine, and I fiddled with it for 10 minutes or so, and I never could get anything close to the right answer. So I guess, I just said, I just guessed. I always guess wrong. I missed one question. That one.
Maybe this is a dumb question or not, but
There's no dumb question.
when you establish the base 10, base 2, or whatever, what's the rationale for deciding that base is going to be?
Well, normally we tend to do things in base 10.
Because it represents
10 fingers. No, really, that's where it came from. And when you go to base 2, it's because of binary logic, it's a 0 or a 1. There's only 2 states.
So it's the difference between analog and digital.
Well,
digital probably more.
It's a different process.
Yeah. Digital is you deal with stuff in discrete quantities or quanta when you get to the physics stuff. Where analog, it's, can't remember the word for it, but it's just continuous. You can keep taking your decimal point out to infinity, essentially. Okay, now you can multiply, divide, add, and subtract exponents. You won't be doing much addition and subtraction, but multiplication and division frequently. So if I've got 10 to the 2 and I want to multiply it times 10 to the 3, I simply add the exponents and it becomes 10 to the 5th. So that's the same as saying 100 times 1,000 is 100,000. If I've got 10 to the minus 2 times 10 to the minus 3, I add them and I get 10 to the minus 5th, or 0.0001. If I take 10 to the minus 2 times 10 to the 3rd, so I got a minus and a positive, I still add them, comes up 10 to the 1, which is 10. Division, you do the same thing except you subtract. So multiplying and dividing exponents is one of the reasons why we use them. It's very easy. And it's kind of like using logarithms. Who here remembers slide rules?
Slide rules.
You got a slide rule?
Substitute.
Oh, I said, who here remembers the slide rule? You probably never saw one.
Nope.
Or we had calculators.
Yeah. It uses logarithms to multiply and divide, like doing exponents. To do addition, you essentially have to normalize them to the same exponent. So if I want to add 2 times 10 to the second plus 3 times 10 to the third, I convert this one, well, one of them, so it's easier to do this one. So that's equal to 30 times 10 to the 2, and I can add it to 2 times 10 to the 2, and it comes out 32 times 10 to the 2. Likewise, if I'm subtracting, I just have to get the exponents the same. So whatever I have to do to get them to the same power, and then I can add or subtract. Okay, reciprocals. Now, use these quite a bit. It's essentially the 1 divided by the number. So reciprocal of A is 1 over A. So if A is equal to 1 over B, then B's 10, then A is going to be 1 over 10. We use this in formulas for some parallel and series components where you don't just add them. So in the case of parallel resistors, which we'll talk about later, the formula is it's the reciprocal of the sum of the reciprocals. It's easier than it sounds. Okay, so you take each value, in this case, say we have 2 resistors in parallel, R1 and R2. So I take the reciprocal of those, add them together, and then I take the reciprocal of that. So in this example, if I add 100 ohms to 200 ohms, I've got 1 over 100 plus 1 over 200, and converting these to decimals, so it becomes 1 over 0.015, and if you do that on your calculator, you'll get 66.667 ohms. Actually, it's going to be 6666 all the way out. The one thing that will help you on the test when you get one of these questions, just to make sure you're in the ballpark, when you have parallel resistors or series capacitors, which is also the same kind of formula, the result is always going to be less than the smallest value. So here, the smallest one was 100. Our answer was 66. If I had made this 2 million ohms, it's still going to be slightly less than 100. If it was infinite, it would be 100. So that's one way to make sure that you're in the right ballpark, because they never, at least so far, have 2 answers on the exam that are close enough together that you couldn't tell which was the right answer from that.
Is this for the old exam or the new ones after July?
The new one after July is the general. The technician changes, I think, 26. And the extra change 24.
So I haven't seen any of this stuff when we haven't studied. Goes this on the new July for general?
Well, definitely this one's on the technician, I believe. I get them since I've done all three and teach them on. I can't tell which one's which. And a lot of the exams cover some previous material. On the extra, you'll have stuff that was on the general and technician. It might be worded different, but it's the same basic stuff. You just get more math and more questions. The extra is 50 instead of 35. Okay. Everybody got reciprocals. A little bit about orders of magnitude, which is another thing just to kind of make sure that you're in the ballpark. And we tend to deal with components by these orders of magnitude, and that's how we represent them. The actual can't remember the word for it, prefix, the value before the decimal point isn't nearly as important as the power of that number. And you also need to, particularly on the test, be able to approximate. You almost never need to do anything to 1% or less. So like in this example, if I got a 1 ohm resistor and 1,000 ohm resistors, it's essentially the same as 1,000 ohm resistor. Same is true for this one. Okay, prefixes. Now these are things that will be on the test and how to convert from one to another. Like if you've got kilo ohms, they might have a question about how many mega ohms is it, or vice versa. Microfarads and picofarads are another one that's a frequent conversion. So these you sort of have to get familiar with and memorize. Normally, there's always something that screws it up, which is kilo. But the large values are capitalized. It's like mega, giga, tera. Forgot what the next one is.
Peta,
Huh?
peta, right? Peta,
I don't remember. I know the opposite is a femto. Unfortunately, kilo is always a small k. I never exactly understood the reason for that, but that's the one that's different, which sometimes is easier to remember. The kilo is 1,000. It's, I guess, from the Latin or the Greek. A kilometer is 1,000 meters. You won't really, in any of the, so far, the exams deal with teras. That's more in the computer world, where you're up to terabytes. But you won't normally see deci in tenths. We deal with centa and centimeters. When you get up to the high frequency stuff, they measure the wavelength in centimeters. On the lower frequencies, it's in meters. If you get up to really, really high stuff, you got millimeters, like radar. Capacitors and inductors will have microfarads or microhenries. They tend to do nanos a lot on the exam. In my 60 years playing with electronics, I never bought a nanofarad capacitor in my life. But because they're either microfarads or picofarads. But they throw this one in just to make it more difficult, another one to memorize. And they all represent, exponents, which is why you need to be able to convert back and forth. And you're almost guaranteed to get a question about that, where you've got something they give you in microfarads and they want you to convert it to picofarads or similar. Where?
I was always taught to do is take the decimal and then it's either a number in front, number of zeros in front, or number of places in it. Behind it.
Yeah, there's some tricks people do to try to remember which way you go. Okay, whether you shift the decimal point to the left or the right. In these, if you notice, they're always three decimal places. So if you're going from picos to nanos, okay, a picofarad, if I shift it, is going to be 1,000 nanofarads. Or excuse me, the other way around. A nanofarad is going to be 1,000 picofarads. And a microfarad is going to be 1,000 nanofarads or 1,000,000 picofarads. So you just have to keep straight which way you're moving your decimal point. And you just need to practice with those. It can get a little confusing, but once you've kind of done it, well, it's pretty straightforward.
We probably have practice questions for this online and send them.
Yeah, you definitely, regardless, before you take the exam, you need to go to one or more of the online practice exams. ARL has one that you don't have to be a member to use, at least for the technician. Most people like hamstudy.org, but I think that may be going away because the guy that does it's retiring. There's 3 or 4 others. I don't have it in here, but I got a chart beginning of the technician class where I list 6 or 7 different ones. You need to do those and score consistently close to 90. If you're getting 90s, you won't have any trouble passing the test. You won't necessarily get 100. You don't need to. You just need to pass. It's kind of like getting an MD degree. You don't have to be the best doctor. You just have to pass. It bothers me.
That's scary.
Okay, logarithms. I can't remember exactly how logarithms were first developed, but it's another means of dealing with very large and very small values. And it deals with ratios. So, for instance, if I want to take the log base 10, because there is a natural logarithm that's to a different base, we don't deal with that one. That's engineering math and stuff I tried to forget. But the logarithm base 10 of 1 is going to be equal to 0. Okay. The log of 10 base 10 is going to be 1. So it's really, in this case, how many zeros this ratio has. So the log of 100 is going to be 2, 1,000 is 3, 10,000 is 4. So they're pretty straightforward. If I asked you the log of 1,000,000, what is it? It's 10 to the 6 or 6. Okay. If it's a small number, then we're going to wind up with a negative value, but the same sort of ratios, reciprocals, basically. So the log of 0.1 is going to be -1. And the log of 1,000 or 1,000th is going to be -3. So you'll see these on signal reports on your receiver, where it'll normally be some signal that's so many dB down. Occasionally you get a positive one. Usually it's a negative one, maybe down 100 dB. When you plot things like filters and amplifiers and stuff, they normally chart that if it's something that's frequency dependent on a logarithmic scale on the frequency, so that you can cover from 0 to light. Sometimes the amplitude, if it's something that has like a filter response particular, that will be done in a logarithmic scale. And we'll usually have it in decibels. Any questions on logarithms?
So it's really just the number of characters to the right decimal point.
Right, when it's nice even tens. Now, if I asked you what the log of 5 was, you'd have to look it up on your calculator, because I don't remember it.
Log of 10 divided by 2.
Huh?
Log of 10 divided by 2.
No, not quite.
Algebra.
Let's do. Okay, decibels. The Bell Laboratories on the Bell system started using the bell, which they named after Alexander Graham Bell, to measure like transmission line and telephone amplitudes and things, because they had very large values. In electronics, it's a way too big a number, so we've gone with the decibel, which is one of the few places you see the deci. We talked about that at 10. So that's a tenth of a bell. But even when we have 10 decibels, we don't call them bells. We just call it 10 dB. And we use this to show the gain or loss of amplifiers, attenuators, your signal noise ratios that you see on receivers. Actually, it can be applied to any kind of ratio. The two basic formulas we talked about before for a power measurement, and which is what we mostly will deal with, it's 10 times the log of the ratio of the powers. If it's a voltage or a current, because of the square function, it's 20 times the log. This will not come up on your test. So this is more of an audio thing where you see it. But this one, you almost guaranteed to get a question about a decibel. Okay, I made this little chart showing a range where we go, let's see, a plus 40 dB, which says the ratio of power is 10,000. Okay. Or the same as 10 to the 4th. Right. So when you do the decibel, and you take that log and you multiply it by 10, okay, you get 40. Because if you remember the other chart, the log of 10 to the 4 was going to be 4. So 10 times 4, so we get 40 dB. Now, if we've got a number that's not a power of 10, like, well, let's go to 3 dB first, because this one you see a lot. It's used cutoff frequencies on filters and things like that. When we use what we call the 3 dB point, where the value is 3 dB less than the normal amplitude. So 3 dB turns out to be a power ratio of 2. Okay. And if I do the log of 2, I get this number, which is why they're not. But if you work it backwards, and I think I did on the next chart, show that it's actually 2. If this was a voltage ratio, it's the square root of 2. Okay. So that's where the other 20 versus 10 comes in. And if we're a negative 3 dB, it's going to be half. So we call that half power, where you're 3 dB down. 6 dB is going to be a quarter power. Now, in voltage or current, you see the 0.707, which everybody remembers as the reciprocal of the square root of 2. It's one you need to remember. That will come up in a lot of stuff, 0.707. Okay. Any questions on decibels? All right. So if we had, we want to know what the gain, let's say, or loss of in decibels of 10 watts to a milliwatt. Okay. Then we do the formula and we plug in 10 watts over a milliwatt, and it's going to come out to be a ratio or 4, okay, times 10. So we get it 40 dB. So you've got 1,000th of a watt, okay, compared to 10 watts, which is 10 greater. Okay, so there's 4 decimal places between them. So that's why it's 4, okay, and then times 10. If we were doing the same kind of thing with voltage or current, it would be the 20 log formula. Okay. Now, to go the opposite way, and I believe this one only shows up on the extra exam. There is a question where you want to go in the opposite direction. You know what the dB is, you want to find what the ratio is. And it's just a matter of taking 10 to the whatever that dB value is, divided by 10, because in the formula it's 10 times. Okay, so we're going to divide it by 10, and you need a calculator for that one, and it'll come out approximately 2, because 2 isn't exactly 3 dB. It's 3.01 something. To confuse you. Everybody good? Lou?
I'm following, but I'm definitely have.
I'm confused, but
A
I'm
lot of
good. Yeah.
equations because I'm used to doing these kind of equations in like an Excel spreadsheet and I can let Microsoft do the work for me.
Yeah, but you can't bring that with you.
I know that, so I'm gonna have to practice on a calculator, these equations.
Yeah. Well, you don't have to do many where you need the calculator. Most of them you can do in your head because they'll use nice numbers. It doesn't hurt to know how to do it. In fact, I've discovered as you get older, it's much harder to remember things where you have to remember how to derive them instead of remembering a lot of stuff. Okay, a little trigonometry. It doesn't show up too much, but a few cases. Just as a refresher, what sine, cosine, and tangent are. And there's something I saw that wasn't on this chart to help people remember it. It was so, ca, tau. SOHCAHTOA. Somehow that's supposed to be easier to remember these, but I'd never come across it before. But out there, if you do a search on the internet, you'll find it a lot. Basically, what you're doing for a given angle, you're going to take the opposite side of this right triangle. It has to be a right triangle for it to work, over the hypotenuse, and that value we call sine. So in a triangle where this is half of the hypotenuse, okay, that's going to be a sine of 30 degrees, or sine is 0.5. Cosine is just the opposite. Okay, we're going to take the adjacent side divided by the hypotenuse. In both cases, sine and cosine, if this is a 45-degree triangle, they're going to be equal to 0.707. There's that magic number again, which is 1 over the square root of 2. All these things are related to 2 and pi. I don't think there's any case where tangent comes up, but it's just the opposite over the adjacent side. Okay, so also when we're doing these triangles where we represent vectors, when we talk about phase or impedance, which is a vector quantity, you'll have some magnitude at an angle, and you can use the Pythagorean theorem to solve for those variables. So it's the old c squared is equal to a squared plus b squared. And you've probably seen where they show a square here and a square down here and one over there, and showing how they relate, make it easier to remember. But, you know, it's just simple algebraic manipulation. So you can solve for A, B, or C, whichever side. And it's always the square root of the sum or difference of the sides, depending on which one you're looking at. This is one, I don't try to remember these. I just remember this and derive them. An example where you use it is impedance, which is a vector of the actual real resistance plus the reactance, which is imaginary. So we put these on the complex plane. Now, I know you don't know that because we're getting to engineering mathematics, and I try to forget that too. But you have to deal with it. And in engineering, we use J to represent the imaginary number, which is the square root of -1. Mathematicians use I. We use J because we use I for current. And we haven't used J for anything. So it was handy. So when you plot an impedance on a rectangular coordinate system, okay, the real value will be on the real axis, and the reactance value is going to be on the imaginary axis. And it can be either positive if it's inductive or negative if it's capacitive. So the impedance is going to be the magnitude of this vector, which is the square root of the real plus the square of the real plus the square of the imaginary. That won't be on the technician exam, but you'll run into this more in the general and extra. Another example of using the Pythagorean theorem is if you're putting up an antenna and it's high enough that you need to put guy wires on it. One way to figure out how long they need to be is knowing the distance from where you're going to put it in the ground or whatever and how high it is, and you can easily calculate how long this needs to be. Just need to make sure you add enough extra for things and not have to do like I did. Had to put it a little higher and add extensions. Okay, this is just an example of the rectangular coordinate system where you would plot vectors. This also comes, and I don't know that it shows up until maybe extra where deal with power factor, which is on your household AC. If you have a lot of appliances that have motors, they'll be inductive. So you'll have inductive reactance. So your power meter that's sitting out there spinning around is driven by the amount of current coming into the house. Now, when you have a part of a reactive load where it's inductive or some cases could be capacitive, you notice that that vector was much longer than the real part. So you have the same thing with if you looked at the current. If you got an imaginary current, and it's going to make the meter spin faster, but it's imaginary power. It isn't real. But you get charged more because you're drawing more current because it takes more from the generator, but you're not getting any extra power. The only real power is what's on the real one. That's why you see, in fact, some NASA guy years ago invented a power factor controller that you could put to fix that. So your meter would correct for it. So your meter would only read the real current or power. Sometimes we use a polar coordinate system, usually in antennas, to show radiation patterns, possibly with impedance vectors where you're going to represent it as a length and an angle. Normally you see it as the real plus the imaginary as a rectangular coordinate. Sometimes it'll represent it as a value at an angle of a certain amount. Okay. Probably the most important constant that you'll deal with is the speed of light. It's a nasty looking number of meters per second. we rounded off or approximated to 300 million meters per second. It makes it a lot easier in the calculations, and it's close enough. The other thing will come up is a coulomb, which is 6.25 rounded times 10 to the 18. I believe that's a billion of elementary charges. An elementary charge is the amount of charge you see on an electron or a proton. One's positive, one's negative, but the value, which is approximately this, okay. So when we get into doing current, we measure current as an ampere is 1 coulomb per second, or a whole bunch of elementary charges per second. Another one is converting inches and millimeters. So instead of remembering 39.4, you can just approximate it to 40 inches per meter. So if you get questions on doing wavelength, which are guaranteed to get one, you can use 40 inches per meter if they want the answer in inches. Usually it'll be in meters. There's also 25.4 millimeters and an inch, which occasionally comes up. We talked about sine and cosine of 45 degrees being 0.707, 106, and it keeps going. Square root of 2 will come up a lot, which is 1.414, blah, 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 blah. And 1 over the square root of 2 is, again, our 0.707 number. This is also used to what we call RMS. Yep. Your AC power in your house. Okay, say it's 120 volts AC. That's RMS. It's actually peak to peak several hundred volts. But RMS is a way to calculate the equivalent power if it was DC. So that 120 volts AC at your house will produce the same amount of power or heat as 120 volts DC. But it's a much higher voltage swing because it's that right. Okay. The square root of -1, okay, like I said, is mathematicians use I. Engineers use J, same thing, just because I is used for current, it's less confusing. A formula that comes in handy, which I actually use a lot, is y is equal to mx plus b, which is the formula for a straight line, the first order. So m is the slope of the line. B is the y-intercept of the line. In other words, where it crosses the y-axis. If b is equal to 0, which means it crosses at x0, y0, then you just got a sloping line. Turns out this is Ohm's law, where that slope is resistance. And this is the current, this is the voltage. We did the Pythagorean theorem, the hypotenuse, and the basic Ohm's law and the power law. Any questions on that so far? Everybody's up on their math.
Yeah, as I said, I think I'm gonna have to do a lot of practice formulas and work that out.
It just takes practice.
I'm shooting for luck.
Huh?
I'm shooting for luck.
That doesn't work. Unless now We had a guy in one of our exams a month or so ago, an old Navy guy, was telling us how he used to pass the Navy exams without studying. And when he got to a question, he didn't know the answer.
And then it was C.
No, it was unique and it might actually work. If he didn't know the answer, he'd look at the clock and where the second hand was, which quadrant, A, B, C, or D, is the number he picked. And he said he passed the tests.
I'm not that lucky.
Wow.
You better hope the clock's not fast.
Well, it's random. It's probably better than your guess. I know it'd be better than mine. I always guess wrong. And then I keep thinking, well, I'm going to guess this, but I should pick the other one.
I mean, I haven't done algebra in a long time, but when I got my pilot's license, I used to use a lot of it, so it's.
Yeah.
Yeah.
Okay. What is electricity? I'm not sure anybody knows, but we call it the flow of energy or current caused by a potential difference. There's some force that's causing current to flow. And it has four main characteristics that we look at: the voltage, which is the force, the current, which is the amount of charge that's flowing, back in the coulombs. Things can have resistance or opposition to that current flow because we only have zero resistance at like absolute zero temperature, because everything that's conductive, like your metals, copper, aluminum, silver, gold, all those will still have some resistance. And then power is the rate of doing work. Okay. So those are the four main things we're going to look at. But first, we'll start with the old atom. And an atom, there seems to be pretty good consensus that there's a nucleus with protons and neutrons in it. And it has an outer, what they call shell, at least in some of the models, where you have electrons that are negatively charged, and they're equal to the number of protons that's in the nucleus. So the net result is a neutral charge on the atom. When it becomes an ion, by getting an extra electron or losing an electron, then it becomes either a positive or negative charged ion. And the elementary charge, which I mentioned, which was at 6.25 10 to the 18th of a coulomb, is approximately what the charge is on an electron, how much it carries. So if you had that extra amount of charge come in to the atom to knock that electron out, okay, then it can go off and combine with another atom, either as an extra or filling a hole where there's one missing. That's how the charge actually gets transferred around. Okay, here's some of the old models. I mean, they first decided, well, atom was this little ball, and then it had positive and negative things in it. And then remember this back in the old days with the atomic energy thing. This is the one we most commonly use for these kind of discussions, where we talk about the electrons being in various shell layers. And this outer layer we call the valence layer. And that's the electrons farthest away from the nucleus have the weakest bond to the nucleus, to the proton. Remember, it's kind of like in magnetism, and even if you do the old comb trick, comb your hair and charge something up and rub a glass rod and charge, you get one positive, one negative. electrostatic and magnetic poles repel and attract, same as here. Electrons are attracted by protons or vice versa, but the protons can't move. And two electrons will repel one another. So when you've got them in the shell, they kind of spread out because they're opposing one another, but they're both attracted to protons down here. So the ones out here are easier to knock out of its shell, orbit, whatever you want to call it. And that's what we'll call free electrons. I can't say much about this model, where I think this is just some cloud and they just wander in and out. And this is a lot easier to deal with where they're discrete layers or orbits.
Yeah, which looks like centrifugal versus gravitational force.
Yeah. Well, the other one was Schrodinger, he's famous for the cat in the box. If anybody's watched Big Bang Theory, they did that. Okay, so here we have a much simpler one, which they don't say what it is, but because it's got 3 electrons and can't really tell. If it was 3 and 3, it would be lithium. So we've got this outer one, which right now it's a neutral atom because they're balanced. If for some reason we get enough energy to knock that electron out of its orbit, okay, it becomes an ionized atom, and it would be a positive ion because it has one more proton than it does electron at that point. If it had captured an extra electron, it would be a negative ion.
It's got more electrons.
Right. And then sometimes they get in the crystal stuff where they're sharing electrons, and we won't talk about that much, except in semiconductors a little bit, part 2. Okay, so this is some of the official definitions of voltage, where they define it as the potential between 2 points of a conducting wire when a current of 1 amp dissipates 1 watt between those points. Now, we haven't talked about amperes or watts much, but these things are all interrelated, so it's kind of hard to talk about one without the other. Another definition is that the potential difference between those 2 points will impart a joule of energy per coulomb of charge. So what that is trying to say is this formula here, where a joule is equal to a watt second. In other words, how much work is done by 1 watt of power for 1 second. Now, hopefully this will be clearer later on. It's probably confusing right now.
Well, I haven't heard you used on anything outside of lightning.
Yeah, we won't do anything on the exams that I can recall with joules, but it's just part of the standard definition, and it is Joule's law. Everybody's got a law. Okay, here's a little animation showing a copper wire, and you have these electrons running around and going from one atom to another, and that's actually happens. They're not static, and how fast that happens is a function of temperature. I start heating that wire up, these become more and more active to the point where they become so active that they're generating photons, which means that that copper wire now is like a light bulb. It's giving off light. So there's a lot of activity. Now, if we apply a potential, like hook a battery up to that wire, okay, this, we'll talk about this a little bit, is actually showing electron flow. And you notice, if you're familiar with a 9-volt battery, this is the positive terminal where it's black. This is the negative terminal. So in some of this things, they talk about electron flow, particularly classes with the military when they're doing this stuff, as opposed to conventional current flow. And I'll talk about the two of them here in a little bit. But really, you need to think of this instead of electrons moving through here as charge. Because in fact, electrons only move a couple inches per second. There's no way an electron at near the speed of light goes around this circle, but the charge does. I might try to make one at some point, but in physics class, decades and decades ago, there was a demonstration where the professor took a long clear tube, filled it with ping pong balls. Okay. And if you tap one end of it, ping pong ball flies out the other end instantly. Ping pong ball didn't travel, fraction of an inch at most, but that force went all the way through, that energy, which is exactly how this works. It's the charge that's moving. So you've got electrons moving around, and it may jump from this one to this one, which leaves a hole, and back and forth. They don't necessarily migrate from one end to the other, but the charges, because it's being attracted by one potential and pushed by the other potential. Okay, so some of the common voltage sources you're going to see, particularly in amateur radio, are batteries with your handy talkie. If you get a technician license, mostly you'll be operating with a handy talkie. So you can get on the air for $30 with a Baofeng. The simplex or the repeater, a lot of repeaters around here you can get to. If you know CW with your technician license, you can operate in some of the HF bands. Probably nobody here knows CW, including me.
And CW license back in the 70s.
Oh.
I can remember that.
I'm trying to learn it, but we'll see.
Yeah. I remember the SOS, that's about right.
Yeah. Well, CQ is the other one you need to learn. Actually, I started to get my license back in the 70s, and I couldn't do the code. I got interested in doing other things. And, we were launching rockets to the moon.
If you were to fly for an airline, you used to have a radio operator's license, and you'd have to learn Morse code.
Yeah, I don't know if that's still true.
It's not.
And they dropped it with amateur radio a number of years ago. Okay, so batteries are classified as non-rechargeable and rechargeable. Your typical flashlight batteries, carbon zinc, are not rechargeable, regardless of how you try, or the button cells in your watches and things like that. We have rechargeable. The most common is the lead acid car battery. Everybody probably has one. Then they came out with nickel cadmium and nickel metal hydrides. Those are mostly replaced nowadays with different versions of lithium, lithium ion, lithium poly, lithium iron phosphate, all kinds. The other main source is your household power, okay, which we call 120 volts AC or RMS. And it's usually a 15 or 20 amp service. And sometimes you may have a 240 volt outlet if you've got big things, or if you get into amateur radio big time and want a 1500 watt power amplifier, probably need a 240 volt circuit to plug it in. Okay, we measure it most of the time with a multimeter. There's things like line voltage monitors, which a lot of people may have. It's just a little meter that displays the AC line voltage. And then there's also laboratory instruments that are precision for measuring voltage, not that common. Most of the multimeters will measure other things like AC and DC, current, resistance. Some cases, some of the newer ones will read capacitance. Most of them don't actually read true RMS. You can buy them, they cost more to actually do true RMS. And what that means is a cheap one, if you've got a perfect sine wave, will give you pretty close to the RMS value. If there's any distortion in that wave, or if it was a square wave or triangle wave, it's not going to come close. Whereas a true RMS, which uses a different technique, is going to be able to read that. Okay, so what did we learn? That free electrons, did I go too far? Okay. In metals is the mechanism that carries a charge from point to point. Right? They're jumping from atom to atom, and the charges are moving, but they don't necessarily go, the electrons don't necessarily go in the same direction the charge is being pulled or pushed, depending on your point of view. And an atom that gains or loses an electron is called an ion, either positive or negative. That voltage is the potential, or EMF, the force that causes the charge to move from point to point. And movement of the charge we call current. We measure it in volts, named after that Volta guy. He discovered a lot of other things. And most common are batteries and household power. Even with amateur radio, if it's not a portable or mobile base station stuff, will run on 13.8 volts. So you need a separate power supply that looks like a battery, basically. Okay, direct current. Old Benjamin Franklin is responsible for a lot of this stuff today. And at the time, they didn't really understand how this stuff works. So he decided that current flowed from positive potential to a negative potential. Well, that's stuck because it was there for years, and it's too hard to change after they discovered that electrons go in the opposite direction, charge goes in the opposite direction. So we call that conventional current flow, and we still use that most of the time. It's only when you get into semiconductors and vacuum tubes where you care about the charge or electron flow. Direct current always flows in one direction, from it's conventional positive to negative. If it's changing direction, we'll call it alternating current. And we'll get into that a little bit later. There's this thing showing conventional current going through the light bulb, and suppose that electrons, which is really charge, going in the opposite direction. Okay, so direct current. Edison was big on DC or direct current and was trying to power the country with his dynamos all over the place, which were DC generators. Nikola Tesla, which you may have heard of, actually worked for Edison, but he was a pretty smart guy, really. He invented a lot of stuff. And one of the things, he was big on alternating current for power transmission. And he also got into trying to do wireless power transmission. He actually accomplished it, but it just wasn't practical. I mean, I probably should dig up a picture of it. The setup he had, and I think he managed to transmit some power, maybe a mile, but it was just an enormous setup and just not practical. He left Edison and went to work for Westinghouse, who also was a proponent of alternating current, and they developed the AC generator and transformers for high voltage power transmission. So you're going to transmit power with a lot less current. So you're going to have less power loss because power is I squared R. So the lower the current, okay, the less loss you're going to have in the conductor. So if you raise it up to 1,000,000 volts, you've got a lot less current. And that's eventually what happened, and Edison lost that one. And we normally measure current. Again, most everybody in the field will have a multimeter. And like I said, it does a bunch of different things depending on how much you pay for it. And one of the more expensive ones you can get will actually do RMS. This is an example of somewhat of a laboratory ammeter. You might use in breadboarding circuits and stuff to measure currents. When you use an ammeter, you put it in the circuit. Okay. Whereas when you're using a voltmeter, you're going to measure the voltage across the battery or across the load. To measure the current, you have to have it in the circuit to measure the current through. Okay, so conventional current goes from positive to negative, electron flow, negative to positive. Direct current always flows in one direction, positive to negative. We measure it in amperes, named after another scientist. And an ampere is equal to 1 coulomb per second. Remember, that's 6.25 10 to the 18th charges. Okay, so the other thing I guess that Edison or Franklin did was use the terms conductors and insulators. And conductor is normally a metal, usually has 1 to 3 valence electrons in its outer orbit. And the farther away they are from the nucleus, the easier they are to move, which is why silver, which has more protons and electrons, is the best conductor of all of them, because the valence electrons are easier to knock out or add to. This electronegativity thing is very confusing, but it's sort of it's the opposite of how easy it is to strip the electrons out. it's not my chart, so I'm not responsible for using that term. But I had to look it up. And I'm still not. It just seems odd. It's more in chemistry. Okay. Insulators have many more valence electrons in the outer orbit, so it's very hard to strip them out, which is where the high electronegativity means. And examples of that are mica, glass, your rubbers, plastics, those kinds of things. Exam question will talk about glass as an insulator. Conductors questions will be about silver, copper, and aluminum. We don't use gold. It is a very good conductor, not quite as good as copper, but it's expensive. But you use it where you need something like you gold plate connector fingers, things like that, so they don't tarnish or oxidize. Okay, the old periodic table. Here you can see copper, which is atomic number of 29, means there's 29 protons, 29 electrons. One in the valence orbit or shell. Silver, 47. And you can see that its valence shell is going to be much farther out from the center because, yeah, and this one doesn't, but it's got more shells, and I think it only has one or two valence electrons. Over here on this side are your look on mine, your helium and lithium, which is why lithium and sodium and those things show up in some of your batteries. Over here in these green ones, you have gallium and indium and some of these things which are used to make semiconductors and substrates in semiconductors. And then, of course, you got oxygen over here, which has some very tightly bound electrons, so it's essentially an insulator by itself. Okay, so there's silver, and you see it's got one valence electron, and it's 1, 2, 3, 4, 5 in the sixth orbit out here. So it's easy to move this electron around. Copper has one also, but it's only got 4. So it's much closer. It's more tightly bound. So it's harder to get it to be free. Okay, so most metals are good conductors. Silver's the best, copper's next, most commonly used because it's cheaper than silver. Because it's got many free electrons. It allows current flow, and that's what we use for connections between electronic components. Insulators such as glass, plastic, rubber, mica is a really good one, which they use in some electronic components like capacitors or as insulators on transistors, things like that. It has very few free electrons. It prohibits current flow, and we use it for isolation or insulation. Okay, resistance. Okay, they define the ohm as the electrical resistance between 2 points of a conductor when a constant potential difference of 1 volt applied produces a current of 1 amp. So basically, they're using a lot of words to describe Ohm's law, where resistance is equal to the potential divided by the current. It was derived by actually experimentation. where Ohm sat down and he took different materials and applied different voltages across it, measured the current through it, and plotted it. And it turned out that it would essentially plot a straight line, your mx plus b curve. And he did it for a lot of different materials, and it was always a straight line, and it always had a slope. So that the slope of that line is what became resistance. Sometimes we use the Greek symbol omega to represent ohms, although most of the time you'll see it written out as ohms in honor of George Simon Ohm. Okay. So resistance is the opposition to current flow. And it's opposition to DC or AC current flow. It's the same. Now, when we talk about impedance and reactance, they're only affected by AC current. Okay, so resistance turns out to be equal to the volts divided by the amperes, and we measure it in ohms. Here's a plot of how similar to how he did it. And for each resistance value, which is the slope of these lines, and I've seen some pictures of his actual plots, and they varied along the line a little bit, but they were essentially a straight line. Okay, here's the pi chart, which I mentioned before, where the theory is if you can't remember the formula, just remember to draw a circle and write those three things in there. So if you want to solve for current, you divide E by R. If you want to find resistance, you divide E by I. And if you want to find E, you multiply I times R. So it makes it fairly easy to remember if you can remember to draw the circle. So if you have trouble with it, as soon as you get in the exam, when you start, turn your answer sheet over and draw your little circle, if you need it. Here's a picture of one of the first resistors. It's the size of a soup can. This is what modern day resistors look like, except it doesn't have any surface mount, which would be hard to see against these. They'd be like grains of sand along here. Oh, that was the other thing I forgot to mention on the electrons and atoms. That there was a thing I read to show you the scale. If you represented the nucleus of the atom as a grain of sand in the middle of a football field, the size of the atom would be the football field. So there's a lot of space between them. Okay, to measure resistance, again, we're using the old multimeter on its ohm setting. For more accurate measurements, a lot of times we use what's called a Wheatstone bridge. And it's composed of two fixed resistors in this bridge configuration. There's a meter between them. This leg has a variable resistor, which you adjust with these knobs. And then you put the part you want to measure between these. And the theory is that when this one equals, these two are equal to each other. When you get this side that you're adjusting equal to this value, the voltage in here will be zero because it's a balanced bridge. So you've got the same voltage drop through both sides. And again, that was named after some guy named Wheatstone. Okay, so resistance, and that's like a test question, is the opposition to current flow. It's the ratio of volts to amps, where we get Ohm's law. We measure it in ohms. Sometimes we represent it with a mega. You use the little chart here to help remember it. Okay, so if I had a 12-volt battery supplying 2 amperes, what's the resistance of the load in ohms? Ooh. Now, these are like test questions.
I know. I'm brain dead.
It would be 6, right?
Huh? 6? Okay. If I got a 10 ohm resistor, it has 1.2 amps flowing through it. What's the voltage across?
12.
Okay. What's the difference between a conductor and an insulator? Well, you wouldn't pass that exam question.
You know, if I go cut that cable over there and you hold on to the copper, you'll know what the conductor is. So the conductor allows the free flow of electrons, but the insulator does not.
Right. What's direct current?
It flows in one direction.
Okay.
From positive to negative, and the electron flow goes from negative.
Right. What's a free electron?
It is the electron that jumps away from the atom.
Right. The outer valence shell, easy to move.
Which is like,
Which is lightning. Actually, lightning is alternating current.
The flash we see is actually the negative charge, isn't it?
It's like I think it's like 3 cycles.
Yeah.
Yeah. And what you see is ionized air. So you've taken electrons away and heated stuff up to where you got a plasma, you got photons coming out and stuff. And it's actually charge going from the ground up.
And that's why I see joules. That's where.
And the most common source of a constant DC voltage. Battery. Okay. Electric fields. Okay, if you have potential differences, you have electric fields. Now, this one isn't the best chart, but it was the best one I found at the time. So if you think of these little circles here as conductors that you're looking head on. What?
Restroom break.
Oh, you need a break? Well, fine. Just, sure.
What's wrong with me?
Okay. It's coffee time anyway.
Motorola, and we do radiation power, cover center. Okay. What's you start to look like?
THC gummies.
Okay. No profanity now. Okay, so if we have electric potential, we have these electrostatic fields, and just like magnetic fields, they oppose and attract. So I think in this one, it's trying to show, if you looked at these as wires and you were looking end on, and you have current going in one, current coming out the other, it's just showing the direction of that field around that wire. Now, as these get closer together, you see where there's, let's assume the blue ones are negative, are current going in, The fields are opposing one another. This is the same thing, but in the opposite direction. And here they're opposite polarities, so those fields are attracting one another. Now, if you've ever seen it's terrible when you get old, you can't remember things. They have a little jar, and I can't remember the name of it, but it's got a rod down the center of the stopper, and there's two gold leaves attached to it. So if you charge that up, like with the comb, and it puts a positive charge, if that's the right one, the gold leaves will actually separate because they're light enough and there's enough force there, it will actually cause them to separate. If you can get opposite charges on them, they will collapse back together. You can actually see that with wires. In fact, what was it? There was something here yesterday or today mentioned somebody shorting a power cable, and it actually drew enough current. The force was able to, it was like zip cord. It was actually able to separate that cord, repelling the thing together.
Because you meant electrons because they're opposed.
Well, it was a short to the two wires, and they just ripped it apart. There's some big forces.
A lightning jar or something?
Leyden jar. That's what I'm trying to remember. Yeah. They do a lot of physics demonstrations with those things. Okay, so these other ones are showing like a wire adjacent to a plate of some sort and how those fields are. If we had two plates, okay, with opposite charges, then you've got pretty much a constant field between them, where this is how a capacitor works. In this one, what you've got, assume this is a wire and you're looking end on, and centered in this conductive tube, which is how coaxial cables work. Somebody got the bright idea, instead of having two wires side by side, where if you don't, like we talked about, twist them to reduce the interference, they're susceptible to outside interference because you've got the other fields can affect it. That if you took one of those and
Wrapped it in an insulator.
made it into a sheet and wrapped it around, okay, you'd contain the electric field within it. Okay, so it's not affected by any field from the outside, either magnetic or electrostatic. And that's how a coaxial cable was developed. So regardless of the whether you got it polarity one way or the other, okay, you've got this field contained within there. So if we have these plates that are separated by a certain distance, okay, with a potential across them, you're going to get a uniform field. And this is what turns out to be what we call a capacitor. So you've got a charge building up on one plate, an opposite charge on the other. So you have this field between them. The strength of the field is going to be determined by the distance between them and the area or surface area of these plates. So we wind up calling that a capacitor because it can actually store energy in that electric field. And how much it stores, and what we call the fact that it can store that energy, we call that capacitance. We measure it in farads, named after Michael Faraday. Everything is named after somebody. And they decided that a 1 farad capacitor can store 1 coulomb, that's all those charges, at 1 volt potential. So, and the amp represents the flow of 1 coulomb per second. So a 1 farad capacitor can hold an amp second of charge at 1 volt, which is how we come up with the charge is equal to the capacitance times the voltage. And in this little picture, we're showing the dielectric in the center, which is another word for insulator, with the 2 plates and the charge on the actual physical formula for calculating capacitance based on the area and the separation of the plates I don't have on here, and that's not part of the test. But it's a fairly simple formula, and you can easily figure out what the capacitance would be if you took 2 pieces of aluminum foil and separated them with a piece of wax paper, and you got a capacitor. One of the early ones, actually, it wasn't Leyden. It's something else.
You got it right.
I don't remember what it's, still don't remember what it's called. But anyway, the Leyden jar is one of the early capacitors. Now, it says that they filled these with water. I'm not sure I understand why, unless it's to make a better connection. But essentially, the capacitor is the foil or the conductor on the inside of this bottle versus the outside. So you have a connection to the in one and one to the outside, and you've got a crude capacitor. Most of the modern ones were made, the earlier ones, with aluminum foil and a paper, like a wax paper separator, and they rolled it up into a tube. And they call those tubular paper capacitors. And they're still around. Like I said, the Leyden jar was one of the first ones. And old Frank Benjamin actually invented one he called the Franklin square, which was 2 square plates of glass separated by, 2 plates separated by a square piece of glass. This is a picture of an assortment of more modern capacitors. These are electrolytics, which process is slightly different because they use an electrolyte to help migrate the charge. So they can actually hold more per volume than the basic electric field type. These are ceramic capacitors, which are 2 metal plates separated by a piece of ceramic. These are what we call air variables, which you use for tuning, basically, having an adjustable capacitor. And it's still 2 plates separated by air. One of them moves, so the plates can mesh together, and how much they overlap determines the amount of capacitance.
And they'll still hold a substantial charge even if disconnected from a power source.
Yeah, if you had one in a transmitter or a matching network for high power amplifier, and you got a few thousand volts across that capacitor, it's got a little charge.
The old cameras, that's how the flash cubes went off, the flash cubes were powered by the capacitor.
Yeah.
That was my first failed experiment.
Yeah, we back in machinery lab in college, we had this big board with all kinds of switches to, big knife switches and stuff to run the great big motors and things. And we'd take electrolytic capacitors and hook them up to the board, turn the power on, blow up. It was interesting. They make a lot of fluff. This is a typical ceramic capacitor where it's got a thin piece of ceramic and they plate some sort of metal on there and make the contacts and then coat it with usually another kind of ceramic to insulate it. It's probably the most common capacitor you'll see. They have it covers all the smaller values and they're cheap. Obviously, it doesn't take much to make them. This is a kind of a cross section of a tantalum electrolytic capacitor. So you've got, I'm not sure how well you see, but this outer, what they call centered tantalum, and an inner, and this centered means it's made up of like ground tantalum that's sort of pressed together. So there's holes in it. It's porous. And then there's an electrolyte in there, and it is what actually carries the charge between the two. But that's typical to an electrolytic capacitor, not necessarily all tantalum. That's more modern. Okay, here's a typical circuit. I'm going to show how we charge and discharge a capacitor. I've got a 10 hertz square wave coming in through this resistor just to limit the current a little bit, and a 1 microfarad capacitor. So when we simulate that, the blue line is our square wave, which is going from 0 to 10 volts. And if you see, the yellow line is the voltage across the capacitor. So it starts at 0 and it slowly charges up. And how fast that charges is a function of the current going in, which we limited with that resistor. Because if I had no resistor there, it would almost exactly follow the square wave and you wouldn't be able to see the effect. Now, once it's charged up, we take the voltage away and it slowly discharges back through the circuit, through that resistor. And this plot is the actual current flow. So you see it instantly goes up to 1 milliamp, which is as much current as we're going to get through that 10K resistor. If I had a 1K resistor, it would be 10 milliamps. And it slowly decreases as the voltage charges. So once it's charged, there's no more voltage or current flow into that capacitor. And that's capacitor at DC can actually act as an insulator or block DC voltage, which you use a lot of times in circuits. Okay, so capacitance, test question, is the ability to store energy in an electric field measured in farads, constructed from conductive plates separated by an insulator. Another test question. Current decreases as the capacitor charges up to the applied voltage. And we talk about the current leads the voltage. Okay. The current goes up instantly. The voltage goes up slowly. Okay. And there's a little memorization thing called Eli the Iceman. where for an inductor, which we'll talk about in a minute, E, the voltage, leads the current. For a capacitor, the C, the current leads the voltage. So that's supposed to be able to help you remember the two of which one has leading voltage, which one has leading current, or vice versa. Okay, now magnetic fields are also created when you have a current flowing through the conductor. So you not only have an electrostatic field or an E field, but you have an H field or a magnetic field. Similar to magnets, okay, you've got that magnetic field and opposites attract and the same polarity repels. So in this one, we're showing conductor with the current going in that direction, and use the right-hand rule. Okay? Your thumb is the direction of the current. Your fingers are the direction of the magnetic lines of force. So, and that's kind of an arbitrary, somebody decided at some point in time. So they're circulating in the counterclockwise direction if you were looking down from it. You have the opposite current over here, so they're going in the opposite direction. Now, when we take that wire and we wind it into a coil, okay, the magnetic lines of force tend to concentrate in that common area between them. Okay, so this is how we build what we call an inductor. Now, a wire by itself has some inductance, but basically you need many turns to get a lot of inductance. And to get even more, you put a material in the core that has what we call permeability, and it can concentrate the magnetic lines of force. In other words, it acts like a magnetic conductor. So it's things like iron or the ferrites and things like that, which have very low magnetic resistance. So this is just showing, again, with the current going through the coil, okay, the concentrated magnetic lines of force. You get a little bit on the outside, but most of it is in the center. This is sort of redundant, but we call this inductance the ability to store energy in the magnetic field, whereas capacitance is storing energy in the electric. So it works the same on the opposite. And this is a typical solenoid type inductor where you've got some sort of magnetic. Usually on these, it's like a ferrite rod. There's another picture of an actual one. This is a toroidal inductor where it's ferrite or powdered iron material in the shape of a donut. Now, the reason they've gone to these is there's virtually no magnetic lines of force outside of that donut. Everything's concentrated in the center. And it makes a nice compact inductor. There's some other forms here where they're wound terms around this little insulated thing. These are surface mount inductors where there's a coil inside of that. These are not to scale. This thing would be maybe 1/8 of an inch square. This is a small inline inductor. Sometimes we call them chokes. It looks like a resistor, but there's actually a little coil in there. This is just another form. Okay, so we'll do the same thing with the inductor. Apply our square wave through a resistor and a 10 millihenry inductor. I picked those so it makes a nice chart. So here we're applying the square wave, and you notice the voltage on the inductor follows that square wave immediately. Okay, and then the voltage decreases to 0. When we take the voltage away, okay, we get an instant polarity change because the magnetic field is where the energy stored is collapsing. So it's trying to prevent itself from collapsing, so it creates a current in the opposite direction. So we see that field in the opposite direction, current collapsing. If we look at the voltage, okay, we see the voltage going from 0 up to, excuse me, not the voltage, the current starting at 0 and going up to the maximum value where the inductor has as much charge in it as it can hold. And at that point, from the DC point, it looks like a short circuit. I mean, it has some very small resistance value, but it's essentially a wire. And that's why you're going to see different behavior with alternating current, because you're hitting this. So it looks like initially, it looks like an open circuit to an AC waveform. So depending on the frequency, and this is the higher the frequency, the more impedance the inductor has. Whereas the capacitor is just the opposite. The higher the frequency, the less reactance or impedance it has.
So the inductor basically works as an inverse to the capacitor.
Yes. And that's how we get resonance coming up shortly. So the inductance is the ability to store energy in the magnetic field measured in henries. We make inductors from coils of conductive wire. The current increases as the magnetic field increases, and the voltage leads the current, the old Eli the Iceman. That question is not on the technician test. It does come up general or extra. Okay, so circuits. We kind of have two. We have analog and digital. We'll talk about digital in part 2. In analog circuits, they're made up of series and parallel combinations of active and passive components connected together with conductors. Your passive components are resistors, capacitors, and inductors. Your active components will be things like tubes, transistors, diodes. I guess you'd even consider things like relays, transformers, although transformer would be passive. Okay, so we start with a series circuit. In a series circuit, like series, all the components are connected together in series. So there's one path through all the components. In this one, we're showing two resistors. We got a 100 ohm and 1,000 ohm resistor. We have an ammeter in the circuit. Remember, it has to be in the circuit to measure current. So we're measuring the current at this point. In this one, we're measuring a current between the two. And in this one, we're measuring the current down here, and it's always the same. because the current through the series circuit is going to be the same through all the components. It doesn't matter where you measure it, you're going to get the same current measure. If it's a parallel circuit, in other words, there's more than one path. Okay. The one thing that's common is the voltage across each of these legs is going to be the same. The current, however, is going to split. So the current at this point, we'll say I, okay, splits off as I1 through resistor R1 and as I2 through resistor R2 and R3, which are series. So we actually have a series and parallel combination circuit. But the voltage across this resistor is going to be equal to the voltage across the battery. The voltage across these two resistors is going to be the same as the voltage across the battery or the voltage across this resistor. Any questions? You're staring.
Yeah, I was thinking about it in my head.
Just feel free to ask. Okay, so
So the voltage is gonna be the same across the path.
that's the key. The voltage, right. On a parallel circuit, the voltage will be the same. On a series circuit, the current will be the same. Okay, so if we have resistors in series, because they're easier to deal with, then we just add them up. Okay, so the total resistance is going to be equal in this circuit to R1 plus R2 plus R3. And if I put substitute values, okay, 1K plus 2K plus 3K is 6K. Simple arithmetic. If I put them in parallel, however, here comes the old reciprocal. So if I have those three resistors in parallel, I have to take the reciprocal of the sum of the reciprocals. So if I substitute, I get 1 over 1K, 1 over 2K, 1 over 3K, which would wind up being 1 over 6K, which if you do it on your calculator or your head, comes out 540 5.45 ohms. And again, you notice the value is less than the smallest value of the combination. It's always going to be smaller. If it was if one of them was infinite, it would be equal. So it's always going to be smaller. So on the exam, that's going to make sure you got the right answer if it's at least smaller than any of the ones in the circuit. Okay, capacitors in series. Now they behave like resistors in parallel. It's the old reciprocal of reciprocals. So you just go through the same exercise, and once again, the resultant value is going to be less than whatever the smallest one was. Now, if they sometimes on a test, they'll give you maybe two. Well, yeah, they'll give you two in series, two capacitors in series with the same value. Now there, you don't have to go through all that. Okay. You just multiply them and divide by the sum, and you come out with basically half. So if that was 6 microfarads and 6 microfarads, the result would be 3 microfarads. Or you could do the reciprocals. But if it's more than, that only works when there's 2, to multiply and divide by the sum. So capacitors in parallel act like resistors in series. You just add them. Okay. Inductors in series act like resistors in series. because each one opposes the flow. So the more of them in series, the more opposition to flow. If they're in parallel, okay, and it's like capacitors in series or resistors in parallel. And you do your little reciprocal formula. Okay, so in a series circuit or in series, resistors and inductors add up, capacitors are reciprocals. Current is the same through all the components in a series circuit. In a parallel circuit, resistors and inductors combine as the reciprocals. Capacitors add, and the voltage is the same across all the components. Okay. There was this guy, Gustav Kirchhoff, who came up with another set of laws. All these guys like laws. And they're used to analyze circuits. You don't really need it for a simple series or very simple parallel circuit, but when they're more complex is where these things come into value. And his voltage law was that if you go around the loop in a circuit, the voltages will all add up to zero. Okay, because in our let me back up. Well, we can use this one. I have a voltage on the battery at this point that's positive to negative. Okay, if I go around this loop, okay, I have a voltage across this. Let's pretend this is a resistor, so we don't have to worry about it changing its value. I have a voltage across this resistor in this direction that's equal to this. So if I go in this direction, I've got a positive voltage and then an opposing voltage. The sum is zero, because I'm going to take this one minus that one. Likewise, if I went around this loop, okay, I've got a voltage this way and a voltage this way. So I'm going with this voltage against this voltage. They add up to zero. Does that make sense? Now, his current law says that the currents flowing into a node connection point must add up to zero. So, I forgot I had this one. Here's the voltage law again. Okay, so we can see that we have E here and V1 across R1. So if we go in that direction, okay, we've got opposing voltages, so there'll be zero. Same thing over here. And this was also showing that the current through these two resistors is going to be the same because they're in series. Now, over here, we have the current law, so we have a node at this point. So I have a current I going into this node, and I have a current I1 coming out and I2 coming out. So those will equal this one, so it's zero. So when you get into trying to analyze circuits, those are very important concepts. Not that you need to know that for the technician exam. Okay, so the voltages around the loop add up to zero. Parallel elements have equal voltages. I should have put in there, series elements will have equal currents, and the currents in and out of the node add up to zero. Need to fix that chart. Okay, power. It's the rate of doing work. We measure it in watts. And work is the amount of energy used in joules. So 1 joule, we said, was equal to a watt second. And this shows how we get all that stuff to the power formula, where power is equal to the voltage times the current. Or if you play substitution with Ohm's law, it's equal to the current squared times the resistance. Or it's equal to the voltage squared divided by the resistance. So they're all things you can derive between the power equation and Ohm's law equation by substitution. So some examples of power calculations. If I got 12 volts at 1 amp, it's 12 watts. If I had 50 watts at 10 volts, there's 5 amps of current. If I had 100 watts at 1 amp, it's 100 volts because I'm dividing power by current. If I have, if I want watts and I know current and I know resistance, I square the current. So it's 2 amps squared times 50, or 200 watts. Likewise, if I want watts and I know voltage, I square the voltage divided by the resistance and come out with 100 watts. This one is some significance because most amateur transceivers, base stations, will put out 100 watts. So into 50 ohms. So that means it's putting out 70.716 volts into that 50 ohm coax. And that's RMS volts. Again, we have, we want to solve for volts. So we take the square root of the watts times the resistance. And if we wanted to do amps, and we knew power and resistance, we take the square root. Remember, an exponent to the -1/2 is the square root.
So if we took like a simple light bulb on, let's a single circuit, so you have a 100-watt light bulb.
Right.
So 100-watt light bulb, 120 volts, you draw 0.83 amps current.
All right. Okay, here's a bigger pie chart, which I don't have copies of, but you could find it on the internet, which relates all of these things together, all the different laws. So if you want voltage, okay, if you know any of these are the equations. If you want resistance, there's 3, depending on whether you know current and voltage, current and power, voltage and power. Same thing for wanting power. So these are all derived from those first 2 equations, the power law and Ohm's law. And I don't remember all those off the top of my head. If I have to, I just derive it again. Because I do remember Ohm's law and the power law. As you get older, you might forget too. Okay, AC circuits. Some components will behave different, like inductors and capacitors, with alternating current than they do with direct current. And they tend to be frequency dependent, where direct current is essentially alternating current at 0 frequency. So it means it doesn't alternate. Uh, we characterize AC with frequency, phase, wavelength, and then we have the components, the reactance, impedance, and then resonance effects, and we combine them. So this was just a little simple thing showing generating AC voltage from this generator versus a battery and switching between the two. I couldn't find much of an example. Okay, so let's talk about frequency. It's a measure of how many times per second the waveform changes polarity. And we represent it in hertz, named in Hz, named after Heinrich Hertz. It also has a period, which is the reciprocal of the frequency. It's how long in time it takes for the waveform to go through one complete cycle. Okay, so how many times it goes through a cycle per second is its frequency. How long it takes to go through a cycle is its period. Like a pendulum clock, okay, the period is how long it takes to go from one side over and back. The frequency is how fast, how many times it does that per second.
We don't do anything to change it in the US, it's fed in at 60 hertz, right?
Right. For commercial power.
Yeah.
Now, like in aircraft and stuff like that, they use 400 hertz. And then Europe uses 50, I think.
But they use higher
Yeah,
voltage.
220, 240, at least in England.
Most of Europe's same, right?
Yeah. And funny plugs.
Depending on what country you go to.
Right. You get a whole set of adapters. Okay. Now, we also will talk a little bit about, and it'll come up later, phase, where I defined it as the fraction of a complete cycle of the waveform. And we can represent it in degrees, where we assume there's 360 degrees in a complete cycle. Now, that's not exactly arbitrary. If you envision watching somebody go by on a bicycle and you watch their foot on the pedal as it goes up and down as they're traveling, it's creating a sinusoidal waveform. So if you actually map circle over to a shifting thing, you can actually plot out by doing the value of the sine at each point you want to pick, plot it, you'll get a sine wave. And that's where that came from and why it relates to 360 degrees in a circle. And also it turns out in math, instead of using degrees, because they're nasty things and a lot of fractions and decimals, since everybody knows the circumference of a circle is 2 times the radius. So we came up with this thing called a radian. So we said a circle is composed of 2 pi radians. And it works out a lot easier in math, where you use 2 pi to represent a complete circle than doing degrees. And you'll see in a lot of these formulas coming up, you'll see 2 pi, which is where they came from, because they're all derived from using radians. They don't talk about the radians in any of the amateur radio stuff, but they do use the formulas, which has 2 pi in it, which is where it came from. But they do teach it in engineering school. And this is just showing what a 90-degree phase shift looks like between these two waveforms. So the peak of this waveform turns out to be at 90 degrees. And the peak of this one is 180 degrees. So there's a 90-degree phase shift between the two. Okay, so the next thing we look at is wavelength. So if we've got a waveform and it's traveling through space, what we call free space, where it can travel at the speed of light. So we define the wavelength as how far it travels in some unit of distance, usually meters, in one complete cycle. We represent that with the symbol lambda for wavelength. So you get the formula that the speed of light, which is a constant, and we use 300 to make it easier, is equal to the wavelength in meters times the frequency in megahertz. And the reason we use megahertz is so we can cancel out the 300 million meters per second. So if we do this in megahertz, it automatically, let's just use the number 300 instead of 300 million. It just makes it easier to do the manipulation. When we're actually talking about circuits, the waveform travels slower than the speed of light. And we have a thing we call velocity factor, which you'll see when we talk about coaxial cable or even wires. To figure out the wavelength, you need to know what the velocity factor is. In other words, what percentage of the speed of light is it actually traveling at through that conductor? In coaxial cable, sometimes it's as low as 0.75, the speed of light. So you need that correction factor, or else your length measurement for the wavelength is off. And in fact, one of the exam questions, you can get the right answer without doing the correction factor. But it'd be close enough that you can guess the right answer. But without, if you use the correction factor, you get the same answer as on the exam. And they're using 0.95 for the correction factor for a normal copper wire.
So is the correction factor given on the exam, or where to know?
In that particular question, yes. Or it's built in. There's another formula, which I didn't put on here. Use 468 divide the wavelength times the frequency, or use those. And the answer comes out in inches because they've already factored the conversion factor in there, and it gives you inches for half a wavelength, which is another one that's commonly used. Because when we talk about antennas, typically you're going to talk about a quarter or half a wavelength. So they use that one because a lot of people like to deal in inches. But it's easy to, if you do it in meters, it's easy to convert. Remember, just assume 40 inches per meter. Okay, so alternating current continuously changes direction. At a frequency is the number of times it changes per second. We normally use a small f to represent the frequency, and we do it in hertz. And we have hertz and kilohertz and megahertz and gigahertz, and then I don't know, terahertz, I guess. I don't deal in that frequency here. We have the phase, okay, where it can be shifted, and you'll see with inductors and capacitors, they create a phase shift. And then wavelength is the distance that it travels during a cycle, based on the speed, which is the speed of light or less, depending on the actual medium it's going through. Okay, reactance. It's the opposition to AC current flow by either an inductance or capacitance. Capacitor or inductor. And they behave differently with AC current. So if it's a capacitor, we call it capacitive reactance, and it's inversely proportional to the frequency. If it's inductive reactance, it's going to be directly proportional to the frequency, which means the higher the frequency, the higher the opposition to current flow. Whereas capacitance, the opposition to current flow is less the higher the frequency. Okay, so the formula for capacitive reactance is one as the reciprocal of 2 pi times the frequency times the capacitance. So there's our 2 pi radians times the frequency. Okay. So that product is the number of radians, circles per second times the capacitance. And here I did a simple resistor capacitor, put a sine wave on it, and varied the frequency. And it goes from 1 hertz up to, I don't know, that was blocked, but fairly high frequency. But you see, the reactance starts fairly high and decreases as the frequency goes up, and it decreases exponentially because it's a reciprocal. Whereas when we do the inductor, it's just the opposite of this, so it will be a straight line. And we got the old Eli the Iceman again to show the phase shift. And we plot the reactance on the negative complex plane. The complex plane is where you plot real versus imaginary on a rectangular plot. So below the line is negative, and that's capacitive reactance. Inductive reactance will be on the positive side. So inductive reactance is the same formula, except it's not a reciprocal. And you substitute L. It increases with frequency, and this would be a straight line if it wasn't a logarithmic scale. But because this is a logarithmic scale, it makes it look like a curve. And, we plot it on the positive complex plane. Okay, so reactance is the opposition to AC current by inductance and capacitance. Pretty sure that's a test question. Or something like that. Capacitive reactance is 1 over 2 pi FC. Inductive is 2 pi FL. And you got the phase shift depending on whether it's inductive or capacitive. Goes 90 degrees one way or the other. Any questions on reactance? We'll come back to it on resonance. Everybody good?
But I'm gonna have to scoot.
Huh?
I have to scoot.
Okay. We don't have much more.
And how long?
Let's see. Well, I hate to guess. I think it's just this and resonance. Okay, so transformers are made up of two or more inductors or coils on a common core, which could be air or more than likely some powdered iron or ferrite material like a toroid. That means that they share the same magnetic field because all the magnetic lines of force are all concentrated together in the coil. There's two coils or more on the same thing. So they have the same magnetic field, and we call that mutual inductance because they interact. We have what we call a turns ratio with two windings in a transformer, and we normally call it a primary and a secondary. You have a number of turns on the primary and a number on the secondary, and the ratio of those is what we call the turns ratio. So if you're doing what we call if you had a one-to-one transformer, which you were just using for isolation, and a lot of times you'll see that in AC utility power used to isolate grounds, it'll have a one-to-one turns ratio. So the same number of windings on both sides. There's no voltage increase or decrease. If it's a step-up transformer, okay, you're going to have more turns on the secondary than you do on the primary. So the primary turns is going to be less. And that ratio will determine how much the voltage is multiplied by. So if it was a 1 to 2, it means if I put 120 volts on the primary, I get 240 volts on the secondary. However, when I do that, whatever current I have on the primary is going to be halved on the secondary because the power into the transformer, assuming no loss, is going to be the same on the output. So whatever the input power is, the output power is going to be the same, even though the voltage and current will be different.
So you're gonna run, let's say, 120 in at 100 amps. And then coming out, it would be 240 and 50 amps.
If that math is right.
Well, yeah, depending on what you're doing. Right?
And a step down is just the opposite. Okay, I'm going to have a lower voltage out, which is what you would have normally seen in older electronic equipment where you got 120 volt AC coming in, and then you want to get, say, 12 volts out. So you step it down to around 12 volts and then regulate it to get 12 volt DC. And in that case, you're going to have more current on the secondary because you got a lower voltage. And this is just a typical transformer circuit with a load with a step-up ratio. And we got the blue is the primary voltage coming in, and this yellow one is the secondary. And this is where 0 is, so you can see that the waveform is twice. Okay. Down here are the currents, okay? And blue, in this case, is the secondary, and yellow is the primary. So you can see that the primary current is higher than the secondary. And also, because of the inductance, there's a phase shift between the primary and the secondary of 180 degrees. There's typical transformers. Again, of course, that's not actually, it only got one winding, but if you had a second winding on there, then it would be a toroidal transformer, like this one. I had trouble finding a decent picture of a lot of transformers. So a transformer is two or more coils on a common core. They have a shared magnetic field, which is called mutual inductance. And the turns ratio is the ratio of the primary to the secondary. And it determines whether it's a step up, step down, or isolation, 1-to-1. So if you've got a step up, you have a higher secondary voltage and higher current on the primary. If it's a step down, you got a lower secondary voltage and lower current on the primary. Okay, impedance, the opposition to the flow of alternating current. So it turns out it's the vector sum of the resistance, which is the flow to opposition to DC current, and the reactance, which is the opposition to AC by an inductor or a capacitor. So this is where we get back to the old right triangle. So we have the resistance on the real axis and the reactance on the imaginary axis. And the magnitude of this hypotenuse is the impedance vector. So, and this angle is the phase angle. So that will be how much shift there is between the voltage and the current. And here I'm just showing how you plot the capacitive and inductive reactances. And the way we learned it in engineering was we always used omega, which is 2 pi f. So it's radians with frequency already in it, just to make it less things to write in the formula. And we can calculate the value of the impedance with the square root of the sum of the squares. Okay. And we plot it as on the rectangular coordinates as the real on the resistance on the real axis and the reactance on the imaginary axis. Okay, resonant circuit. It's an LC circuit. There's a combination of inductance and capacitance. At a certain frequency, it will resonate. He talks about it similar to like a tuning fork. Okay. And what happens is you've got energy stored in the capacitor. Okay. When it gets up to where it's charged up, then that charge decreases and that current starts charging up the inductor. So the energy is going from the electric field to the magnetic field and then back again. And this goes back and forth. If there was no loss, then it would oscillate forever. In order to keep it resonant, like to create an oscillator, you need to provide enough feedback to compensate for the loss to keep it oscillating. Because in the real world, there will be some resistance in both the capacitor and inductor. So you'll lose some of the energy as heat. So it's resonant when both the capacitive reactance and the inductive reactance are equal and opposite. So they cancel one another. So if you do R plus Jx sub L minus Jx sub C, and if X sub C and X sub L are equal, then impedance is equal to resistance. They cancel out. And that's the frequency that happens is where it will be resonant. The formula for resonance is the reciprocal of 2 pi times the square root of the product of the inductance and capacitance. That one you need to remember. Pretty sure it's on the tech test. Definitely on the other. Okay, so this little circuit, I like this one because it's showing the energy going back and forth between the two. And current changing direction. This is just an example of if I had a 1 microhenry inductor and a 1 microfarad capacitor, the resonant frequency is going to come out to 159.155 kilohertz. And here's that circuit with a 1 microfarad capacitor and a 1 microhenry inductor. And we applied a sine wave to it. And you can't read it here, but at 159 kilohertz is where, and this is a series circuit, the voltage across these two components goes to 0. And the current, okay, goes from basically 0 up to its maximum value, limited by this resistor and the amount of voltage. And over here is a plot of the impedance, if you calculate it, and this is just 1 divided by the other. So you can see that the impedance goes down to 0 at the point where it's resonant. It's kind of hard to see on that one. Okay, this is a parallel circuit where the inductor and capacitor are in parallel instead of series. And here we have the voltage across this combination, and it starts out at basically 0 or almost, and goes up to its maximum value where it's equal to the input voltage. And you see that the current is going to go to 0 where it's resonant. The difference between a series and a parallel resonant circuit is that resonance, the series circuit, looks like a short circuit, 0 impedance. A parallel circuit at resonance looks like an open circuit or infinite impedance, which you can't ever get infinite because it's real components. And this was a little calculation of, at that frequency, how the impedance changes. Turned out this is what we call a very high Q circuit. So it's a very narrow band where it's resonant. Okay, so impedance is opposition to AC current flow. It's the square root of the sum of the squares of the real and reactive components. The resonant circuit test question is composed of series or parallel LC components. Capacitive reactance is equal to the inductive reactance when it's resonant. There's the formula again, which is the reciprocal of the radians times the square of the product of inductance and capacitance. In a series resonant circuit, the impedance is low at resonance. Parallel, it's high at resonance. So that determines, when you're doing a circuit like an oscillator or something, of whether you want it to pass a waveform at a resonant frequency or block it, depending whether you use a series or parallel circuit. Okay, Lou, made it.
I gotta run.
Any questions?
Yeah, do a lot of studying.
Huh?
I have to do a lot of studying.
Just do the practice test.
Yeah. I think the big thing is just memorizing the formula. Once I get the formulas memorized, I'll be able to do
Yeah.
calculations.
Well, it depends on what you consider the hard part. For me, I mean, I've been an engineer for 60 years. None of that stuff was a problem. Some of it I had to refresh for the extra. The rules and regulations are a pain in the butt. Because that's just memorization. Well, not so much that, but lots of rules and regulations, and you don't know why, it just is. So, for me, that was the hard part.
Have you looked at the series resonance?
Okay, series resonant. Oh, I don't want to go there. Previous. Okay, this one.
Thank you, I just wanted to look at it.
Did you do the formula? Oh, okay. Yeah, I did these and I'm still learning it. Signed up for a thing called Circuit Lab, which they have a free version or almost free version where you can do this stuff, but they limit you to 10 components. So you're kind of limited as what you can do. But for $6 a month, you have unlimited components. And it'll do a lot of simulation. There's a bunch of them out there. And I've tried several. This is one of the easier ones to use, but it doesn't have some capabilities I'd like to see. But for the most part, it works pretty well and it's easy to use. I mean, you can easily build a circuit. They have a whole list. And we'll do more of them on part 2, where we're actually going to do circuits and talk about transistors and diodes and tubes, just because it's on the test.
Yeah.
And at the end, get into digital logic, but do filters and mixers, oscillators, talk about receivers and transmitters, how they work, and put the pieces together.
I mean, the last time I thought about a lot of this stuff, probably be a great technology class for doing this next. So it's been a few years.
Oh yeah, if you don't use it, well, you forget.
Huh? That's why I try to simplify everything in my head when I do the circuits, I just kind of think of like a light bulb on a simple circuit.
All right,